Okay, good evening, and welcome to AGU, to New Orleans, and especially welcome to NASA's Hyperwall. I'm Mike Freilich. I'm the director of the Earth Science Division in the Science Mission Directorate at NASA, and I'm going to give just a brief but very wide-ranging introductory talk. If you hang out around here in the spaces between your sessions, then you will be seeing a whole variety of NASA and other scientist talks on this amazing visual hyperwall. At NASA, we are really stretching the cutting edge of science, if I can mix some metaphors there. We are putting high technology instruments, not only imagers, but also other science instruments, and measuring some random nearby star, like our sun. Next, please. We are sending robotic spacecraft that are incredibly capable to planets that are not so far away from here, like Curiosity on Mars, and you'll be hearing talks about that. Next, please. We are making amazing high-resolution images and taking other data from larger planets that are farther away, like this Juno image of Jupiter. Next, please. And these Juno images from a close approach of the spacecraft to Jupiter, showing unbelievable and amazing patterns in Jupiter's atmosphere, enough to make a fluid mechanician just die of happiness. And we'll come back to that. Next, please. We're making imagery of perhaps the most majestic planet in our solar system, Saturn, from the Cassini mission, which after a couple of decades just ended a few months ago. Next, please. And in imaging Saturn, Cassini also took a bit of a family portrait of our solar system. And you can see other planets, Mars and Venus. And if you look real carefully down in the lower right, next slide, please, you can see this pale blue dot that perhaps someone approaching our solar system and calling us exoplanets would undoubtedly be attracted to Saturn, but then they might see this other blue thing and wonder, why would somebody be an Earth scientist instead of a solar system scientist? But in any event, a planetary scientist. Next, please. Jim Green is giving the next talk, and he'll actually go into detail on these. We are making measurements of our incredibly complex home planet from a variety of different vantage points. This is the EPIC imaging camera spectrometer on the Discover spacecraft, 1.5 million kilometers away from Earth on the Earth-Sun line, so that we can see the entire sunlit hemisphere of the Earth all the time. And of course, if you're 1.5 million kilometers away from Earth, you're farther out in space than the moon. And so on occasion, the moon gets into the picture. And what you see here, of course, is the far side of the moon. We call it the dark side of the moon. It's the side that faces the sun. You figure that one out. Next, please. And moving in towards the moon, the Lunar Reconnaissance Orbiter is taking, again, spectacular imagery of not only the moon that it's supposed to be looking at, but occasionally of our home planet. Next, please. But I'm the director of the Earth Science Division, and if I talked more about what other divisions were doing, all of my people, most of you in the audience, would run me out on a rail. So we are using the unique vantage point of space to take measurements of, to understand our planet as an integrated system, not simply one mission measuring one process, but many different missions, all flying at the same time in low Earth orbit and other orbits, making measurements of many, many different quantities, all at the same time, so that we can understand the interactions between processes and not just individual processes, because it's those interactions which define our complex planet and our environment. And we're presently flying about 16 major missions and instruments as NASA research missions, not counting all the other Earth-observing satellites from other agencies and other nations. Next, please. And from these satellites, from these measurements, we are taking high precision, high resolution, long duration, consistently processed measurements of all aspects of our planet, such as the extent and the evolution of the ozone layer, the stratospheric ozone layer in the southern hemisphere, year by year, over decades, so that we can understand whether the Montreal protocols are indeed working, and they are. Next, please. We're making measurements, excuse me. There we go. See, when I grew up, we didn't have amplification systems, so I just scream. We're making measurements of other aspects, key aspects of atmospheric composition, such as carbon dioxide. And we are taking those measurements from the satellites and assimilating them into atmospheric models that bring together the measurements and the dynamics that we have. And you can see how over this 1 year record of carbon dioxide concentrations across the globe, you can see how atmospheric dynamics and highly exaggerated Earth surface topography are influencing not only the regional but also the vertical distributions of important greenhouse gases like carbon dioxide. Next, please. And we are measuring the growing things on our planet. This is a 2-decade-long, consistently processed, multi-satellite animation of plant growth, greenness on land and in the oceans for the Earth. And I could spend 3 hours talking about this. You can see the march of the seasons with the Sahel in Africa. You can see the influence of flooding, for instance, from the Amazon, bringing nutrient-rich waters into the western tropical Atlantic. You can see the impacts of northers, winds that blow down through the gaps in Central America, mix the ocean, and cause plankton blooms. You can see all kinds of stuff. Occasionally, you can see snow falling seasonally. This is our planet, the living things on our planet, at the base of the food chain, with high spatial and temporal resolution from the vantage point of space. Next, please. And we can also use very high sensitivity measurements to measure weird lights that are coming out from our planet at night. The other part of the living things on the planet, from the base of the food chain to the top of the intellectual food chain. Night lights over the world. This is not only useful for seeing where humans are distributed, these data are being used for things like understanding the impacts of hurricanes in Puerto Rico and the rebound, such as it is, of the infrastructure. You can see where the humans live and where the humans don't live. You can see this bit of light down here with a very sharp cutoff. This is not an island. This is South Korea, and this is North Korea. You can teach a whole sociology course from the night lights. And this is all coming from very, very high sensitivity radiometry instruments on SUMI NPP and other satellites. Next, please. And we are making measurements of the changes in the Earth, especially in the polar regions, which are most sensitive to our changing environment. Measurements over decades of the extent of Arctic sea ice. I don't show it here, but we also have measurements of the thickness or estimates of the thickness of the sea ice. Not only is it going away, it's getting thinner. And that means that the atmosphere is having more of a control than the ocean does as time goes on. Next, please. In the southern polar region in Antarctica, using high spatial resolution measurements over relatively long periods of time from a variety of instruments, we watched as an iceberg the size of Delaware broke off in July of this year from the Larsen C ice shelf. But we followed, with the satellite measurements, we followed the crack over time. Interestingly enough, it broke free in July. There's no sun in July. But these are infrared images because the ocean temperature is different from the ice temperature. They're somewhat lower resolution, but they show clearly when this Delaware-sized iceberg broke off and how it's evolving. Next, please. Using radar measurements from many different countries and many different satellites, NASA researchers have tracked quantitatively the velocities of the ice sheets over the entire Antarctic continent. And you can see the ice moving from the interior of the continent to the oceans. When the oceanic ice sheets go away, the sea ice goes away, it's like removing a cork, perhaps, from a champagne bottle. Beer is over there, by the way. And we need to understand how the dynamics of the land ice might change in the absence of sea ice. Next, please. And we are using many different satellites all at the same time to measure rapidly varying phenomena like precipitation over the Earth with the Global Precipitation Measurement Core Observatory and Constellation. If you get seasick, it's time to go to another booth here. Okay? For the first time, we are making measurements with sort of 10-kilometer resolution and 30-minute temporal sampling, or resolution, I should say, of precipitation over the entire globe, using measurements from many different instruments on many different satellites and combining them. I like to say that before GPM, the only thing we knew about global precipitation quantitatively is wherever I was going on vacation, it was going to rain. Next, please. And we are making measurements and then assimilating them into models that have high precision and high accuracy because we understand the processes, measurements, and model predictions of the two great fluid systems on our planet, the atmosphere and the ocean. Those are really what define our planet's environment. And you can see the ocean is a turbulent liquid. It's not the sort of Gulf streams that you learned about in school. It is full of turbulent eddies. Next, please. And I remind you, no, I'll remind you in a second. And we have complete eddy resolving ocean models now of the entire globe. What you see here are the surface velocities and the temperatures. And you can watch the Eddy field, which is statistically accurate, if not exactly accurate at the time. You can watch the eddies evolving in places like the Gulf Stream, in the equatorial regions, the Kuroshio off of Japan. And I remind you, look carefully at this, and then at the next slide. Do you see any similarities? What we learn about the Earth, what we know about the Earth, I mean, fluids are fluids. Schrodinger doesn't change depending on whether he's in Jupiter or here. Next, please. And finally, with high resolution, high precision, high accuracy, dynamical and composition models, global models of our atmosphere, we can look at the interactions between the dynamics and the meteorology. This is this past hurricane season, and you can see the hurricanes going through. I'm a little bit over time, but come back at a different time, and you can see all of the major hurricanes this particular storm season, and you can see the dust and the salt and the black carbon aerosols in the atmosphere and how they may be impacting the formation and evolution of the extreme weather systems themselves. Next, please. And finally, with the measurements of many different quantities that we have, the models that codify all that we know about the dynamics, the thermodynamics, and the chemistry, we can start to predict with accuracy, globally and with high resolution, how our planet and our environment is evolving. Okay, this was the overview. Now we're actually going to have substantive talks that really explain the science behind portions that I went over here. They will be going on over the entire time that we're here at AGU. When you can tear yourself away from sessions, come down here and see the amazing stuff that NASA scientists are doing portrayed on the Hyperwall. Thanks very much.